Hello everyone and welcome back. I am Hossein Fazilatpour, your presenter for today. To be honest, I am very happy, genuinely delighted to upload this video once again for you after the internet shut down, and hopefully I get the chance to upload more videos for you guys. The English language teaching will also continue. I need a bit more time, but in this channel they would be divided into different playlists so you can consume the media you want. If you want the English teaching, you can go and visit there, and if you want the AI stuff, they're still on a different playlist for you as well. In our last session, we explored the nature of intelligence, especially how predictive processing and prediction error form the backbone of artificial intelligence. However, to understand how AI actually functions in a clinical setting, we have to look at its primary field, data. Well, in this video, we are moving from pixels to data. We will examine the digital nature of medical imaging, defining exactly what digital means, and in contrast to the analog world. It is important to realize that without digitalization, the AI revolution we have witnessing today would be impossible. We will trace the journey of how a physical biological signal is captured, how images are represented as discrete numbers, and how this transition from analog to digital laid the essential groundwork for computer vision and diagnostic AI in modern medicine. In a technical sense, digital refers to a system defined by discrete symbols. Unlike the fluid world, digital systems break information into discrete, countable units, commonly binary symbols of 0 and 1, so they're generally numbers. The defining characteristic of a digital system is the use of a finite set of values. Digital signals have no gray area, they exist in one state or another, like in electrical circuits. It is either on or off. Analog signals. On the other hand, the analog signals represent information through continuous physical quantities. For example, a dimmer switch can slide to an infinite number of brightness levels on your light bulb, off, full, dim. These quantities vary over an uncountably infinite range, making them sensitive to noise and electrical fluctuations. The waveforms at the bottom illustrate this difference. The analog signal on the left is a smooth, unbroken wave representing the raw physical reality, like the pressure wave of an ultrasound pulse. The digital signal on the right is a square wave with sharp transitions showing the system jumping between fixed numerical values, let's say zeros and ones. In essence, analog represents the continuum of reality, while digital represents its quantification. This conversion into stable, discrete numbers give us the reliability and computational power of the modern age. When we look at the various imaging modalities, MRI, CT, PET, or ultrasound, it is easy to see them as entirely different technologies. However, from an engineering perspective, they all converge on a shared electronic logic known as the universal signal chain. As you can see here, our fundamental challenge is that the human body communicates in analog. The physical phenomena we detect, whether it's radiofrequency emission in an MRI coil, the acoustic echoes in an ultrasound transducer, or the scintillator captured photons in a PET scan, are continuous, extremely weak, and inherently noisy. At the detection stage, our hardware is essentially trying to catch these faint physical whispers and convert them into measurable voltages. Because these raw signals are so low in amplitude, the next phase is critical: amplification and filtering. We aren't just making the signal louder, we are aggressively maximizing the signal to noise ratio to ensure that the diagnostic information isn't lost to background electrical interferences. Following this, the application-specific section, using tools like variable gain amplifiers or VGAs and multiplexers, normalizes the signal to prepare it for the most pivotal moment in the entire chain, the ADC. It is very important. The analog to digital converter is the definitive gateway. This is where we leave the fluid, infinite world of analog and enter the discrete numerical world of digital. Only once the signal has been quantized into bit streams can the data and image processor begin the heavy mathematical lifting, the reconstruction, and the AI driven analysis that turns raw numbers into a recognizable internal structure of the human body. This transition from a physical phenomenon to a quantifiable dataset is what ultimately makes modern digital diagnosis possible. Well, while the electronic pathway is universal, the initial detection stage must be highly specialized to capture diverse physical phenomena used in medicine. Each modality uses a unique sensor to translate a specific physical event into an electrical voltage our system can process. MRI, let's say, it is the magnetic resonance imaging. The RF coils detect radiofrequency signals emitted by hydrogen protons returning to their resting state after magnetic excitation. Ultrasound, transducer arrays composed of piezoelectric elements capture echoes of high frequency sound waves reflective of tissue boundaries. Digital X ray and CT, those scintillators and collimators convert high energy photons into visible light for digital sensors in X ray and track X ray attenuation in CT. PET or positron emission tomography. Scintillators paired with photomultiplier tubes or PMTs capture gamma rays produced by positron annihilation. PMTs provide the necessary amplification for these tiny bursts of light. Regardless of the measurement, sound, magnetism, radiation, the sensor output is analog. Each signal is a continuous, weak electrical whisper that must enter the amplification and filtering stage to be rescued from the noise. Now, the analog to digital converter or ADC. ADC represents the definitive transition point where physics meet computation. Up to this stage, components like RF coil in MRI and scintillators in PET captures conditions the continuous analog waveform. However, these voltages are incompatible with modern computational architectures. The ADC resolved this incompatibility through quantization. It samples the analog signal. Sample is important. In the next video, we're going to talk about sampling as well. It samples the analog signal at precise intervals, translating infinite physical variations into a discrete bit stream. This converts the patient's body into a quantifiable dataset. In medical imaging, precision is paramount. Errors or lack of resolution at the ADC stage propagate through the system, potentially creating artifacts, misinterpretation by radiologists, or AI models. By bridging the gap between the noisy analog environment and the high-speed data image processor, the ADC provides the numerical foundation for complex image reconstruction and diagnostic analysis. The data image processor. The data image processor transforms raw digital bit streams into clinical tools. Let me give you some examples, like algorithmic image reconstruction. It takes discrete numerical data from the ADC and performs complex mathematical transforms like FFT for MRI and for CT to reconstruct a special anatomy with back propagation. We also have post-processing. Post-processing and enhancement. It applies digital filters to improve contrast, reduce noise, and sharpen edges, optimizing the image for human interpretation. Interface for AI. Well, it provides a high computational environment for deep learning models and CAD algorithms, computer aided, to identify pathologies using quantified data. Dynamic range mapping. We will talk about it later on. It maps high bit depth data from the ADC to a visible grayscale by windowing, by leveling, to reveal tissue densities. And also data compression and archiving, especially the DICOM. It efficiently encodes massive imaging datasets into formats like DICOM for high fidelity storage and transmission. In essence, the data image processor converts raw digital data into meaningful medical maps. Now, I want you to bear with me. Many parts of what I talked about might be familiar for clinicians. Now, it's going to get a little bit mathematical, but bear with me. It is essential and necessary. It is very foundational for clinicians to really understand the numerical representation and how an image is represented in a computer system. because the foundation of all images is numbers, and AI is manipulation of numbers, binary representation of numbers. Well, think of every tiny processor component as a light switch. On is 1 and off is 0. Combining these represents any number, letter, image, video, sound, everything. Well, to understand binary, consider our daily system. We use decimal or base 10. We use 10 digits from 0 to 1. Each digit's value depends on its position based on the power it has. Consider number 13. It's not just 1 and 3. 3 is in the ones place, okay? Let me show you. And 1 is in the tens place. So we calculated 1 multiplied by 10 in the power of 1 plus 3 multiplied by 10 in the power of 0, which eventually gives us 10 plus 3, which equals to 13. In decimal, each column increases by a factor of 10. In binary, since we only have 0 and 1, each column increases by a factor of 2. You can also see what I mean here. Now let's talk about the construct of binary numbers. Starting from the right, the first digit is 10 in the power of 0, which ones. The second is 10. The third is 10 in the power of 2, the 10 in the power of 3, and it goes on and on. You can also see how number 18, for example, is represented. When we have 4 decimal digits, we can represent any value from 0 to 9,999. Binary follows the same logic but uses power of 2 instead of power of 10, as you can see here. The position represents 2 in the power of 0, then 2 in the power of 1, then 2 in the power of 2, then 2 in the power of 3, and each digit can be either 0 or 1. We call them bits. With fewer options per slot, our range is smaller for same number of digits. With 4 binary bits, we can only represent values from 0 to 15. Now that we established the theory, let's look at how we practically build numbers using a 4-digit binary construct for simplicity. This is a row of 4 slots where each slot can hold either a 0 or 1. Calculating the range. Well, with 4 bits, we determine the value of each position using the power of 2 to the 0 to 1 to 2 to 3 to 4, etc. Okay. Mathematically, this gives us 2 in the power of 2, 16 total combinations. And since we are starting with 0, this represents the decimal values from 0 to 15. Think of it this way: when every slot is off 0, 0, 0, 0, it is 0 in decimal. When every slot is on 1, 1, 1, 1, it is 15 in decimal. The shift to the left pattern, it is important. You can see as the yellow color here. As we count upward, we notice a distinct pattern called the shift to the left. We start at 0, 0, 0, 0, and it represents 0, and then it would be from the left to the right, it would be 0, 0, 0, 1, and it represents 1, as you can see here in decimal. When we need to represent 2, we run out of room in the first column, so we shift the 1 to the next position on the left, resulting in the 0, 0, 1, 0. This happens again at 4, at 8. Every time we hit a new power of 2, we shift to a new column to the left to hold that higher value. At the summary table, if you look at the table, you can see how this combinations builds up. From 0 to 7, the leftmost bit, the 8th place, remains 0. From 8 to the 15, the same pattern repeats, but the leftmost bit switched to a 1. By the time we reach 15, every bit is filled 1, 1, 1, 1. You can take a screenshot as well. Now let's go one step further. Binary to decimal conversion. Well, reading the annotation, if a number has a small subscript of 2 at the end, like 100110 with a subscript 2, it means that the number is in binary. Our goal is to find the decimal representation of the 6-bit sequence that we have here. Here is the step-by-step conversion. Place each bit in its corresponding slot and assign it a power of 2, starting from 2 in the power of 0 on the far right. Then we map the bits, as you can see here. 1 is multiplied by 2 in the power of 5, then 0 multiplied by 2 in the power of 4. And you know that when we have zeros, we do not need to really calculate it because 0 multiplied by anything is 0, and 1 multiplied in any number is that number. And it's a simple summation. We calculate the decimal number by multiplying each bit by its positional value and adding them, which here amount to 38. So the key takeaway is, even though the binary string of 100110 looks longer than 38, they represent the same quantity. The binary version is how computers store it, use it, and manipulate it. Now let's talk about signed numbers. Up to this point, we only looked at positive integers. However, real-world data isn't always positive. For instance, in medical imaging, like CT scans, the Hounsfield unit used to measure radio density can be negative values, such as the value for the air. To handle this in digital systems, we need a way to represent signed numbers. And before that, let's define MSB and LSB. MSB is the most significant bit and LSB is the least significant bit. Before we can represent negative values, we must understand the geography of a binary sequence. We use two key terms to describe the weight of bits based on their position. MSB, or most significant bit, this is the leftmost bit in the sequence. It has the greatest positional value and influence on the total number, which is why we call it most significant. LSB, or the least significant bit, this is the rightmost bit. It has the smallest positional value, and so its significance is lower. Significance in signed numbers. Why does this matter? When we move from unsigned numbers, where all bits represent a positive value, to a signed number, the MSB takes on a special role. In many systems, the leftmost bit is repurposed to tell the computer whether the number is positive or negative. If the most influential bit is reserved for the sign, it fundamentally changes how we calculate the total value of the string. And you can see the positional location of MSB and LSB. Okay, now let's go to explore further. Now that we understand the positional bits, we can tackle how computers handle negative values. In a signed number construct, we reserve the most significant bit, especially as a signed bit. This tells the system the nature of the number. A 0 in the MSB indicates a positive number. A 1 in the MSB indicates a negative number. And also, we can distinguish between MSB and the signed number. The signed number can be the leftmost, and then the most significant bit would be the one adjacent to it. Second complement method, it is very, very easy, so I'm gonna just tell you what it is. You just switch the bits. If it's 1, it turns to 0. If it's 0, it turns to 1, and then you will add 1 completely to the overall number. So the second complement method is to actually represent negative values mathematically. Computers use a process called the second complement or two complement, also known as the two complements or twos complements. It's a simple two-step recipe to convert a positive number into its negative counterpart. Invert each bit, change every 1 to a 0 and every 0 to a 1, and add 1 to the resulting number. For positive values of 0 through 7, the binary remains the same as what we learned, with the 0 leading the way in the sign bit position. So if we say that the sign bit, the leftmost one, is the sign bit, then MSB changes. If we have a 4-digit construct, as we have here, we only are left with 3 that's going to determine our value, and 1 is reserved for the sign. However, when we look at the negative value, things look different. For example, -1 is represented as 1, 1, 1, 1. Following the pattern down, look at the -8. It is represented as 1, 0, 0, 1. Take a closer look. 7 is 0, 1, 1, 1. If we complement it, it would be 1, 0, 0, 0. Then we add 1. It would be 1, 0, 0, 1, representing -8. If we take the number 7, as we discussed, it is how we calculate it. I've left a do-it-yourself section in the middle of our table. Try using the two-step second complement rule to figure out the binary code for -4, 5, -6, and -7. And it's the best way to see how the logic and the sign bit inversion works in practice. You can also pause the video. We have something like IEEE. What is it? It is Institute of Electrical and Electronics Engineers. So far, we focused on whole numbers, but in fields like physics or medical imaging, we often deal with very large or very small fractional numbers. To handle these, computers see floating point representations, which is essentially the computer's version of scientific notation, as you can see here. The scientific notation analogy, think back to how we write large numbers in decimal. Instead of writing out every digit, we might write 3.14 multiplied by 10 in the power of 2. Computers do the exact same thing in binary. Value equals to sign multiplied by significand multiplied by base in the power of exponent. For example, a binary floating point might look like 1.011 multiplied by 2 in the power of 3 in the binary form. The three core components, every floating point number is stored in three distinct parts. The sign, just like integers, this tells us if the number is positive or negative. The exponent, this determines the range. It tells the computer how big or how small the number is by moving the binary point left or right, and we have a fraction part or the mantissa. This determines the precision. It stores the actual digit of the number and dictates how accurate that number can be. Approximation and precision. It is crucial to understanding that computers store an approximation of these numbers. Because binary is based on powers of 2, not all decimal fractions can be represented exactly. And this introduces a balance between range, how high we can count, and precision, how many decimal places we can accurately track. In high-stake environments, understanding these small rounding errors is vital for data integrity. Oh, floating point representation. Well, here is how a computer is going to represent 0.15625 in memory using a single precision or float32 format, which uses 32 bits. Well, constructing the 32-bit element or string, we have this one sign bit located at bit 31 indicates the sign of the number. 0 means positive. We have the exponent. These bits, it is 8 bits, and these bits control the scale of the number. And in this example, the binary sequence represents an exponent shown by e of 1 to 4, which even applied to the standard formula e minus 127 results in a multiplier. And then we have fraction and mantissa, which is 23 bits. These bits define the precision of the value. In this case, the binary translates to a fraction of 1.25. Computers provide a 32-bit float provides roughly 7 digits of decimal accuracy. This is relevant today because LLM weights, the knowledge inside AI models, let's say, are typically stored in floating point formats to balance performance with intelligence. And probably you saw that. We have single precision, double precision, quantized, int 8, int 4, quantization aware, so they're helpful. And you can see here what I talked about already. Now let's talk about floating point number representations. Comparing precision levels, depending on the need of the application, we generally use 3 different tiers of precision: 64-bit or the double precision. This format uses 11 bits for the exponent and 52 bits for the significand. It provides roughly 16 digits of decimal accuracy, but is slower to process, a 32-bit or single precision. Using 8 exponents bits and 23 significand bits, this float 32 gives about 7 digits of accuracy and is significantly faster for general tasks. 16-bit or half precision. This uses only 5 exponents bits and 10 significand bits. While less accurate, it is incredibly fast and memory efficient, which is why it's popular in modern AI and machine learning. The golden rule of programming. There are 2 critical warnings to keep in mind when working with these numbers. Never compare floating points with equal, like exact comparisons, because these numbers are approximations. 2 values that should be equal mathematically might be slightly different in binary. Instead, we check if they are close enough within a tiny margin of error. The 0.1 problem. Well, why we cannot have an exact binary form for 0.1 in decimal. It is similar to how we cannot have 1 divided by 3 exact number in our decimal or base 10 system. And the last topic that we're going to discuss, and thank you for sustaining this. I know it might be a bit confusing and hard, and I hope that I made it easy for you. It is very important because we're going to talk about hexadecimal. Well, hexadecimal means base 16. And as you can see here, we have 0, and then we have to 9. And then we'll have A, B, C, D, E, F. What this means? Well, we mastered binary, but as you've seen, binary can become incredibly long and difficult for humans to read. To solve this, computer scientists use hexadecimal, a base 16 system that acts as a convenient shorthand for binary. The base 16 logic. The name tells you everything you need to know. Hexa means 6 and decimal means 10, giving us a base 16. In this system, we need 16 unique symbols. We use the standard digits 0 through 9, but once we hit 10, we switch to letters A, B, C, D, E, and F. This means A represents 10, F represents 15. Because we start our count at 0, these 16 symbols cover the entire range of a 4-bit binary nibble. Construct and conversion. Just like decimal uses powers of 10, binary uses the power of 2, hexadecimal uses the power of 16. The first position on the digit is 16 to the power of 0, 1. The next is 16 to the power of 1, 16, followed by 16 to the power of 2, representing 256 in decimal, and 16 in the power of 3, representing 4096 in decimal. Now, let's look at the example, 2A7. To convert this to decimal, we multiply each digit by its positional weight. 2 multiplied by 16 in the power of 2 plus 10 multiplied by 16 in the power of 1 and 7 multiplied by 16 in the power of 0. Then we add 512 plus 160 plus 7, and it will give us 679. I hope you get it. You can pause, you can take a screenshot as well. To conclude our discussion on numerical representation, let's look at one of the most common real-world applications for hexadecimal, digital imaging and color or intensity. Well, whether you are adjusting the brightness of a medical image or designing a website, you're interacting with these hex values. Converting to hexadecimal, let's look at how we convert a standard decimal number into a hex using the number 59 as an example. Let me show you. So we divide 59 by our base. It gives us 3, and the remainder is 11. The number 11 is represented by letter B. Therefore, the decimal number 59 is written as 3B in base 16. Well, there's a perfect mathematical marriage between binary and hex when it comes to memory. A byte consists of 8 bits, which can represent values from 0 to 255. Conveniently, 2 hexadecimal digits also represent exactly 0 to 255. This means 2 hex digits, 1 byte of data, making it the perfect shorthand for memory storage. Color and grayscale. This system allows us to define the depths of an image. Imagine that we have a 1-bit image. It is only either black or white, only 2 options. In 8 bits, we could have 256 levels of grayscale. In 12 bits, we could have 4096 levels of grayscale, often used in high-detail medical imaging. For full color, let's consider the standard RGB. RGB represents red, green, and blue. By assigning 8 bits per channel, we create 24-bit colors, which allows for over 16.7 million unique colors. For example, pure standard red can be written as 255,000 in decimal, or simply FF0000 in hexadecimal. You can see it here. So thank you for the time. In the next video, we're going to talk about sampling, aliasing, and much more. Thank you for your patience. Please share and subscribe, and I hope that you find this video helpful.